And before actually I take up this topic, I wanted to understand that this is a topic common to both physics and chemistry. Have you learned thermodynamics and physics?
They haven't yet, ma'am.
They haven't read, right?
Yes.
Yeah. So you will observe that this is a common topic, but from chemistry point of view, see, there are certain common conceptually, some common topics are there both, but we approach in chemistry from the chemistry point of view, the reactions point of view, and there you look into the physical changes and you make it as a universal study. That's the difference. So basically, what is thermodynamics? Look at the name thermo. Thermo means what? What do you mean by thermo? Anything? Does it convey
Heat, ma'am.
heat? So basically, thermodynamics is what? Thermodynamics is a study of energy relationships. Okay? You study about heat energy, there's interconversion of energies, all that you learn in thermodynamics. Okay? So let's understand some terms related to thermodynamics first. So the first and foremost thing is, what do you mean by a system? What do you mean by a system? A system is anything under observation. Okay? And what is surrounding it is known as surroundings. So let me put it in a simple way. Okay? What's the simplest way of understanding it? See, let's observe this. You are sitting in the classroom now. Okay? You are attending your chemistry class, thermodynamics class. Now, if you consider this as a system, what all would be the part of the system? Tell me. You're attending your thermodynamics chemistry online class. Okay? You're in a part of this system. So, who all would be the part of the system? What all would be the part of the system? Tell me. What do you observe? What are you observing around you related to the thermodynamics class? You see that there is a system in front of you. There's a computer system. You see that classes happening on online. So who are all part of this online class? Everyone will be the part of the system. Who are all there? Prasanna, myself, each in your fellow students who are all attending this class. And if you're seeing that on the screen, there is a thermodynamic, I'm showing you the PPT. Probably some other screen you must have opened it, but that will not be the part of the system, isn't it? See, you opened a different page, right? Something else is running on your behind in your laptop, right? That will not be a part of system. What all would be a part of system? The part of the system will be everything associated with this thermodynamics class. Can you get that? Yeah. So you must have opened some other book, like physics book or something else. Something, so many things are around you, but all that related to this thermodynamics only will be a part of your system. So system is anything under observation. The best way to take it is, suppose you are asked to calculate, find out the melting point of ice, and another student is given a task of finding out boiling point of water. So what is your task? Your task is to find the melting point of ice. So will a student who's finding boiling point of water on another table, or maybe he's sharing the same table also in the lab, will he be the part of your system? No. Because what is that your task is? Your task is to find the melting point of ice. That's it. So are you getting it? So system is anything which is under observation. You're observing it. And what's around you will be the surroundings. So the person who is doing the boiling, who is finding a boiling point of water, the other student, what would he be considered as? He'll be a part of? He'll be a part of?
Surroundings.
Surroundings. And system plus surrounding. System plus surrounding will make universe. In your set theory, you have no. If I have a set A, what is not set A? I call it A prime. What would A and A prime together constitute?
Universal set.
Now see, A is your system, A prime is your surroundings. System plus surroundings will constitute the universe. Got it? Is that clear? So let's see some more terms. You have types of system. You have an open system, you have a closed system, and isolated system. So what is an open system? Open system is something which can exchange matter as well as energy with the surroundings. See, for example, you take a water, a trough of water, keep it outside, maybe keep it in the sun. What do you observe after some time? Some time, not necessarily be 10 minutes, 15 minutes. I'm telling over a period of time. It can be a day or 2 days or maybe a month, whatever you observe. What do you observe? Will the level of water remain same?
Evaporate.
Yeah. So now what is water? How is water interacting? Water is exchanging matter, isn't it? Some water is being evaporated. It's exchanged with the atmospheric gases. It is interacting with the atmosphere, isn't it? It's the atmosphere around the trough of water will be its surroundings. Everything around water. So it's interacting. And is there a transfer of energy? Will there be? Will there be a transfer of energy? How?
Heat energy.
Come again?
Heat energy.
Yeah. How is it interacting? Evaporation, condensation, what is all this? Isn't it? How does your water cycle work? You must have learned it in your lower classes also. Water cycle. How does water cycle work? It's the same thing. It's interacting with atmosphere. It's an open system. So absorbs heat, the water gets evaporated. When it releases heat, water will condense. So there is an exchange of matter. There is an exchange of energy. So this is a completely open system. Is that clear? Got it? Closed system. Okay. See, in the PPT, I would have given some examples related to chemistry, the way we do it in the lab. But what I am actually giving examples is a daily life, whatever you observe. Okay. So, what is a closed system? Closed system is something where only energy is transferred but not matter. Okay. See, in this diagram, what you see is there is you know, a reaction taking place in a closed system. Okay, there is carbon dioxide and you see calcium oxide are combined, they are heated together. What will calcium oxide and carbon dioxide give? Together? It will form?
Calcium carbonate.
Calcium carbonate.
Yes, calcium carbonate. It will form calcium carbonate. So this is formed in a closed system. Okay, you will understand the importance of closed system when you go to equilibrium chapter. See, simple. Another example. You fill a water bottle and you keep it in the refrigerator. Right? Will there be any remove water? Will water be exchanged in the sense? Will there be any increase or decrease in the level of water when you fill a water bottle completely and keep it inside the refrigerator? No, it remains the same unless or until you take it out and consume it. Right? The level of water will be same. But what is happening? You observe that water has become cold. The water bottle has become cold. So what is happening there? It's a closed system. There is only a transfer of energy. There is no transfer of matter. Can you get that? Same thing. You keep the water bottle in a hot sun. What will happen? After some time, the water will become warm, right? Totally. So there's an exchange of energy. There's no exchange of matter. Is that clear? Is that understandable, students? Next is isolated. Isolated system, what is it? It's totally, it's separate. It is no way interacting with the surroundings, either in terms of energy or in terms of matter. It's neither exchanging energy nor exchanging matter. So best example for this is your thermos flask, your vacuum flask. What happens to vacuum flask? For considerable amount of time, whatever things you keep, whether hot or cold, it will remain in the same state inside the thermos flask, right? Of course, over a period it changes because you keep opening the lid and you keep closing it, there will be exchange. The heat will pass through. So exchange of energy takes place. So invariably, isolated system, what happens? It will remain in a state where no heat energy or no energy nor matter is exchanged. Is it clear? Vacuum flask, thermocol, thermocol box. Thermocol box is used to mainly carry ice cubes. Okay. And if you observe, in the lab, right? The lab technicians, they use a thermocol box to keep the ice, and they will carry their equipments or they carry their chemicals because there should not be any, transfer of energy or matter inside that. So it will give you a protective state. So it will not allow the energy and heat to be transferred. It's a perfectly insulated vessel. We call it as it is insulated. It's sealed. It's not allowing the heat or allowing the matter to be exchanged. Okay. The next term we have is state of a system. State of a thermodynamic system is it's a measurable macroscopic properties. What do you mean by macroscopic property? Something you measure at the macroscopic level. Then what is microscopic level? What is microscopic level?
Things we can't see with the naked eye.
Which one? Indeed, you people have learned it.
Electrons, protons.
Yeah, we call it as a quantum level. Another name we use there is a quantum level, if you're aware of it. So that's a microscopic level. What is a subatomic level is a microscopic level. Is it clear? It's a quantum level. Now, what we are seeing, remember if you have learned this, what is that, Heisenberg's uncertainty principle, or you would have learned about de Broglie, you would have said that it's applicable for us subatomic particle like electron. So that's a subatomic level is a microscopic level, quantum level. Now, when I'm saying macroscopic properties, what we are invariably, observing normally. Okay. So like this involves measurements of pressure, temperature, volume, heat. All these are microscopic. Okay. So we use P, V, T, and one more you can use is we also use number of moles. Okay. It's amount of substance. Number of moles refers to amount of substance. Everything comes under macroscopic. But in thermodynamics chapter, we use PVT as the main macroscopic property. See here we said amount. Can you see? It is mentioned. So other things will include anything you measure at the macroscopic level, like densities. So many physical quantities you will measure at the macroscopic level. Are you getting it? All those are macroscopic properties. Right? And these are also known as the state variables or state function. So what do you mean by state variable or state function is, this depends on the initial and final values, not on the path. Final values only, not on the path. See, best example I'll give you is, consider you have a gas having a volume V1, okay? And finally, it's going to a volume V2. Okay? Or maybe you have a volume of liquid V1, it's going to a final volume V2. So, what way there is a transformation from V1 to V2, the path is not important. What matters is the change in volume will give you the, actually what is important. It's of more significance to us. Okay. Suppose you have 10 ml of water and the final volume is coming to 100 ml. How did this 10 ml go to 100 ml state is not important for us. It's least important. What is the initial volume? 10 ml. What's the final volume? 100 ml. So what's the change in volume? What's the change in volume? V2 minus V1. 100 minus 10. How much is it?
90.
90 ml. Right? So how did we, arrive at this 100 ml, or how did we arrive at this change 90 ml? We are least bothered. Is it clear? It doesn't matter. It's of no significance. So such functions or such variables which depend only on the initial and final values, final states, not on the path, are known as the state functions. Okay. And as far as this entire chapter is concerned, so let me tell you, we consider a system of ideal gas as your thermodynamic system. In this chapter, throughout this chapter, we take ideal gas as a system. Okay? Anything that is interacting with this ideal gas will be considered as the surroundings. Okay? So here where, before I go to the next topic, I would slightly deviate, introduce you to the concept of gas laws. Okay? Is that clear? So a little bit of introduction. What is an ideal gas and what are gas laws? I hope you know what are gases and the properties of gases. I don't have to tell you that. You've been studying in lower classes also, like what are the properties, the characteristic properties of gases. Like gases compress, gases have a least intermolecular force of attraction. All that you know. Got it?